Good afternoon. My name is Tim Larson, and I am indeed an instructor at Moberly Area Community College here in Missouri. I also got my PhD studying global helioseismology. However, I started the sonification of solar harmonics project with a couple of composers, these guys, Seth Schaefer and Elaine DeFalco. And Rick told you that my presentation is going to be a little bit different, and the main difference is that this is a presentation for everybody. You're going to understand everything I'm about to tell you, and everything I'm going to show you is freely available for download, and all of you can download it and use it. So, the oscillations that Sasha was talking about were actually first discovered in 1960. When it was seen that the surface of the sun was moving up and down with a period of about 5 minutes. And eventually it was decided that this oscillation was explained as the result of sound waves trapped in the solar interior. So yeah, that's right. The sun is actually a resonant cavity for really low frequency sound waves. And because these sound waves propagate through the interior, the frequencies tell us about what's going on inside the sun. So although we've been studying this data for decades, we almost never listen to it. But now the SOCH project has developed a software tool that lets everybody do just that. So as I said, the strongest of the sun's harmonics have a period of about 5 minutes, which corresponds to a frequency of only about 3 millihertz, which is far, far below the range of human hearing, which is usually in the hundreds of hertz or maybe thousands of hertz, which is already pretty high. So if you want to measure a 5-minute oscillation, it's common to make a measurement once a minute, which would correspond to a sample rate of 1/60th of a hertz. However, an audio player will not give you any audio sample rate less than about 8,000 hertz. So in this situation, that means that you got a minimum speed up factor of 480,000. And at this rate, a year's worth of data, you could hear it in about a minute, which is one of the major advantages of sonification. However, often this transposition factor is too high, and so one of the things the SOCH tool lets you do is to shift the frequency independent of the sample rate. And as long as you transpose every one of the solar harmonics the same, then the musical intervals between them will be preserved, which obviously is of interest to composers who might want to use the sun as a musical instrument. So back to the science, helioseismology, how it works in general. We start with velocity images of the sun's surface. We decompose each of these images into its spherical harmonic components. More on that in just a second. For each of these spherical harmonics, we make a time series of its amplitude, and then we do an analysis to measure its harmonic content, basically just figure out how much of each frequency is in that time series. And because the different harmonics inhabit different regions inside the sun, here this shows the depth dependence. You can see how some of them stay close to the surface while others of them penetrate more deeply. And so it's because the different harmonics inhabit different regions that we can use their frequencies to infer things like solar rotation inside the sun. Now, I'm going to play for you a unfiltered time series. This is a single spherical harmonic time series to show you what we're starting with. So this is all the frequency contents playing at once. Not very pleasant to listen to, right? Oops. Okay, good. So the surface behavior of a solar harmonic is a special function of latitude and longitude, which we call spherical harmonics. Spherical harmonics are described by two integers. They're L and M. L is the number of node lines on the surface of the sphere. A node line is simply a place where the amplitude is 0. That's what these white lines in the figure are. And the harmonic degree L tells you how many total are on the surface of the sphere. M tells you how many there are in longitude, and so the number in latitude is simply L minus M. Now, there's also nodes in the radial direction, but of course we can't see that. We only see the surface. So on the next slide, I'll show you some examples of radial eigenfunctions which give the interior behavior, and they're described by a radial order n, which gives the number of nodes along a radius. So here's two examples. On the left, I have plotted n equals 3, just so you can see it. You can see the three circular. You can see the three. I lost the cursor. You can see the three circular the three node circles. But this mode actually has a frequency that's too low for us to measure. I plotted it so you could see it. Over here on the right is n equals 20. This is a mode we could easily measure, but as you can see, the nodes become too close to each other near the surface to see at this scale. But in any case, the important thing to remember is that the total harmonic will be a product of a spherical harmonic, which is a function on the surface, and this function of depth. It's the two multiplied together that give you the total mode. So here's an example of how the mode frequencies, or how the different harmonics inhabit different regions of the sun. So on the top row, we have the surface view for L equals 25, starting from m equals 0 going across. You can see as m gets closer to L, that the mode stays closer and closer to the equator. And down below, I have the same two values of n, 3 and 20. And you can see that as you go up in frequency or up in n for a given L, that the mode goes deeper. So now, the spherical harmonics, we have a different spherical harmonic for each L and M. But to measure n, we've got to do some Fourier analysis, form a power spectrum. What I've shown you here is actually an amplitude spectrum zoomed in on just one value of n for an L of 10 and M of 0 that I chose at random. So the blue line here is the data, and the orange line is the fit to the data. And so the thing about helioseismology is it works all in terms of mode parameters. So basically, it studies the orange line here. And typically just the peak frequency here is what we use for do helioseismic conversion. We measure the amplitude and the width of this peak. But as you can see, there's a lot more going on here. A lot more information contained in the data than is captured by this simple mode fit. And that's what the SOCH tool allows you to do. It allows you to listen to the actual data that we took. And what's shown here is a good example of a filter window that we might use. So what we do is we zoom in on a mode in frequency space, and we set all the other frequencies to 0, and then we transform back into the time domain. And the result would be something like this. This is, again, L equals 5, M equals 3. And I just picked n equals 17 and 21. These have been transposed by a factor of 135,000 and brings them up to about 375 and 448 hertz. So just an example. So far we've used data from two instruments, the same ones that Sasha was talking about, MDI, which took data for 15 years at a cadence of 60 seconds. In 2010, it was superseded by HMI, which takes data every 45 seconds and is operating still today. Now, MDI has been sonified sporadically in the past. In fact, by Sasha himself, who was the one who most famously did it. But now that can be done interactively. And so far, the SOCH project is the only people who have sonified HMI data and the only sonification of 2 full solar cycles of data spanning both instruments. So moving forward, already available is the SOCH-Pi visualization package. It made most of the figures that I've showed you. We're developing a mobile app to give people a way to explore the way the amplitude of modes varies inside the sun. My collaborators are working on planetarium presentations in virtual reality environments, where you can, with ambisonic audio, to spatially separate the different modes. My own personal ambition is to maybe use some of the experience I've got in sonifying global helioseismic data and maybe use it to sonify local helioseismic data. And so maybe one day it could be possible to hear a solar flare. But very soon, what's coming up real soon is we're going to be flooding SoundCloud with all kinds of nature sounds, but of the sun. And so very soon we will find out just what people can hear in it. Thank you very much.